Having seen the power of non-determinism in the design of finite automaton, we shall next look at NFA with epsilon moves. By allowing epsilon moves, we can increase the power of finite automaton in the sense that from the design perspective. So we should be able to get the design in quick time. But later we will show that as far as the language acceptance is concerned, just like class of languages accepted by NFA is same as class of languages accepted by DFA, class of languages accepted by NFA with epsilon moves is same as class of languages accepted by NFA without epsilon moves. So just like we have shown, NFA is equivalent to DFA. Later we will also see that NFA with epsilon is same as NFA without epsilon. Then why non-determinism, why epsilon, all this is helping us in getting the design in quick time. Okay, so that's the advantage. And as far as the language acceptance is concerned, they are all one and the same. Okay, now the fundamental question is this: can finite automaton make a transition or make a move, make a transition without reading any input symbol? So you have sigma, and without reading any symbol from sigma, can a finite automaton move from one state to another state? Okay. So that's the question. Answer is yes. For example, I am at Q0 and I say that on reading epsilon I go to Q1, and on reading epsilon from Q1 maybe I go to Q2. In addition to that, we may read other symbols as well, maybe 0 here, and either epsilon or read a 1, we go to Q1, and I stay at Q1 and read 0 or more ones. So what this says is the following: since we allow epsilon moves, now an input symbol A belonging to sigma can be interpreted as follows. I can see it as epsilon A. This is same as A. You can also see it as A epsilon. This is also same as epsilon, epsilon, epsilon followed by A. This is also same as A epsilon, and so on. So which means when you allow epsilon moves as part of the design, things like this should be taken into account. So reading just A is also same as reading epsilon A or A epsilon, because you are reading an empty string concatenated with a symbol or some meaningful string, you will still get the string. And similarly, one can read any number of epsilon before reading A, or any number of epsilon after reading A, or it may be like epsilon epsilon A followed by epsilon epsilon. So all this should be taken into consideration as far as the design is concerned, because we allow epsilon as well along with symbols like 0, 1 and so on. So now you may ask, when I read a 0, where will I be? It is not just Q0, it may be Q0, or you can even see it as 0 followed by epsilon, so I can go to Q1 as well, or 0 followed by epsilon epsilon, so I can go to Q2 as well. So what am I saying? When you look at delta of Q0 comma 0, I am saying this can be seen as delta, because I am writing a string, delta cap of q naught comma 0 epsilon, or this can also be seen as delta cap of q naught comma 0 epsilon epsilon. So this will tell you, if you just see 0, output state as q naught. This tells you that if you see it as 0 epsilon, then output as q1, then output as q2. Which means when you say delta cap of q naught comma 0, it is actually q naught, q1, q2. The reason is this 0 can be interpreted as just 0, or it could be a string 0 epsilon, or it could be a string 0 epsilon epsilon. Okay, and so this should be taken into account when we design and when we talk about on reading a symbol 0, what is our output. Okay, and in this case epsilon 0 does not appear, otherwise epsilon 0 should also be taken into account. Okay, so something like after reading an epsilon, say one more epsilon, I go to a state called q3, and then q3 I read a 0, which means even this should be interpreted. So delta of q naught comma epsilon 0, this says go to q3. Okay, so now when we talk about an input symbol, one has to take epsilon into account. That can come as a prefix or a suffix, and it can be any number of length of the prefix or suffix. One cannot bound, because you can have any number of epsilon before reading a 0, or after reading a 0 you can read any number of epsilon. So now this is telling you something interesting. So you are at a state and you are interested in knowing, can I read the symbol 1? Can I read a symbol 2? In general, can I read a symbol A? Now this says you may read so many epsilon before you actually read a A. Or after reading A, you may read so many epsilon. So now this brings you something interesting. We are going to define something called E closure or epsilon closure. Just for my convenience, I'll use E of Q, which means epsilon closure of state Q. So what this says is states that are reachable from Q by reading one or more epsilon. So I may read just one epsilon and I may go to Q1, or I may read multiple epsilon then go to Q2. So what all states you can reach? States that are reachable from Q by reading one or more epsilon. So what all states one can reach by reading just epsilon, not just one, many copies of epsilon. Now that should be taken into account when we talk about the design, when we talk about delta cap of q0 comma 0, because you may prefix with any number of epsilon, you may suffix with any number of epsilon, because without reading an input one can make a transition. So when you allow NFA with epsilon, so this prefix embedded with so many epsilon, suffix embedded with so many epsilon, that should be taken into account as part of the design before we actually read a symbol. So which means when you say what would be the output when we read a symbol A, we should also take into account what would be the sequence of states without reading a symbol before we actually read the symbol of our interest. And that is precisely what is captured through epsilon closure. So what we will do is we will define epsilon closure for a couple of examples. Then we will get into how to design missions which will have kind of NFA without epsilon and or kind of conversion from NFA with epsilon to NFA without epsilon. And why is this powerful? We will look at a couple of examples or applications where NFA with epsilon moves will give you quick design. And subsequently one can use our conversion to get NFA without epsilon, then use subset construction to convert NFA without epsilon to DFA. Okay, so let's discuss epsilon closure. Consider this finite automaton. On reading a 0, we stay here. On reading an epsilon, we go to Q1. At Q1, we read a 1. On reading another epsilon, we go to Q2. Q2 is our final state. Over there, we read 2. So sigma is 0, 1, 2. This is a classical example which you will find in Hopcroft-Ullman text. Now for this automaton, we are going to define epsilon closure. So epsilon closure is defined for each state. What all states one can reach starting from Q0 just by reading epsilon. States that are reachable from Q1 just by reading epsilon. Similarly, states that are reachable from Q2 just by reading epsilon. Okay. You may remember this delta of Q comma epsilon, or it is correct to use this delta cap because we see this as string or empty string. So without reading an input symbol, one can stay at the same state. Suppose in your design there is no epsilon at all. Then you ask this question. For example, something like this. So Q0, on reading a 0, we go to Q1. Let me stay here for 1. Let me stay here for 0. For 1, we come here. Now you ask delta cap of Q0 comma 0 0 because 0 0 is a string. Then you say that Q0 comma 0 is Q1, Q1 comma 0 is Q1, so we say Q1. This is a string. On the similar line, now one can ask delta cap of Q0 comma epsilon because epsilon is an empty string. So this says Q0 because without reading a symbol, I can stay at the same state. Same is the case with Q1. In fact, for any state, this is true. So for all Q belonging to the set of states, delta cap of Q comma epsilon is Q itself. Without reading any input symbol or with reading an empty string, we say that we stay at the same state. But if you look at this, epsilon itself is part of the input, or you can look at it this way. Our sigma has got 0, 1, 2 union empty string. So which means we should also see states that are reachable by reading the input symbol epsilon. Over here we see epsilon as just empty string, and epsilon is not part of our sigma input alphabet, whereas for NFA with epsilon, sigma epsilon is part of sigma or input alphabet. So simply saying delta cap of q naught comma epsilon is q naught will not work here, because there are states that you can reach by reading the epsilon, which is why we define something called epsilon closure, which is set of states reachable by reading just epsilon. So starting from q naught, we know that q naught comma epsilon is q naught, because we have seen this. If you read an empty string at q naught, you continue to stay at q naught. In addition to that, you say that you can reach q1, you can also reach q2, which means you can see it as epsilon epsilon, what all states reachable from q naught by reading epsilon. So on the similar line, epsilon closure of q1 comma epsilon is q1. In addition to that, you can reach q2. So epsilon closure of q2 is q2, and there is no further transition from this on epsilon. So epsilon closure of q2 is q2 itself, which means for all q belonging to capital Q, Q belongs to epsilon closure of Q. Fine. So let's look at one more machine. So Q naught, on reading 0 this, epsilon we go to Q1, on reading epsilon we stay here. Okay. Then from this we come back. And there are other transitions. You can assume this one as a final state and this one is also a final state. Now for this mission, if you define E of Q naught, by default Q naught will be there. In addition to that, you can reach Q1. You can also reach Q2. Epsilon closure of Q1 is, by default Q1 will be there, but over here there is a transition on epsilon as well, and anything else on epsilon, can I reach Q2? No. Can I reach Q naught? No. Let's look at epsilon closure of Q2. By default Q2 will be there, and in addition to that you can also reach Q naught, so it is this. An automaton like this, where there is no epsilon at all, but one can still define epsilon closure. So E of Q naught is Q naught, because empty string is implicit. Over here it is explicit, which is why we look at the implicit part as well as the explicit part. Implicit part is the state itself. Explicit part is states that are reachable from that state. So E of Q1 is Q1 itself. It is never the case that epsilon closure of a state is empty for any state, because by default Q is part of this. So now this epsilon closure will help us when it comes to design, and this will help us when we read a 0 and what all states one can reach, when we read a 1, what all states one can reach, all that to compute the output state of delta of q 0 comma 0 or q 0 comma 1, the epsilon closure will be of use, which we shall see next.